15 instructions or so, added a few instructions to the one that was in the book that we were using. But anyway, we talk about hardware. In this case, we're talking about emulated hardware. What are the advantages of emulated hardware? Like I used to tell my students, if you build an emulated CPU like this, one, you don't ever smoke anything. Two, you can put it on a floppy disk and take, or flash drive or Google Drive or whatever, take it home and show it to your mom. If it's hardware in the lab, we'd probably hang on to it, okay? Anyway, I think it's some really neat things. What we're going to talk about today is how CPUs work. And to use as an example, what I want to do is talk about this little CPU I've designed. It's a 4-instruction computer. It has an 8-bit data bus and a 10-bit, an 8-bit address bus, a 10-bit data bus. It has 4 instructions, and we'll talk about what that really means later on. But with those 4 instructions, I could do pretty cool things. The reason it's kind of nice to have 4 instructions is we can build a machine language program pretty easily. In fact, I do that in my classes all the time. We'll build a little machine language program. If you try to do that with an x86, it gets to be really, really, really messy. Okay? So let me just run this for a second, then we'll start in the PowerPoint presentation. What I've got is a little CPU. There's the memory up there, so we put a program in memory and data in memory. Over there is a program counter that keeps track of what instruction we're running, and there's an address bus driver, address buffer. We pull an instruction out of memory, we put it in an instruction register, and split it into 2 parts, one part that's an operand and one part that's an operation. The operation is one of these 4, so it takes 2 bits to have an operation. Over here is what we call the arithmetic logic unit. Here's an accumulator, so this just has one general purpose register. We can bring a number into the ALU and another number from memory, add them together, and put the results back in the accumulator. Anyway, it's a real computer. It only has 4 instructions, and then to kind of make it so we can do input and output, I memory map so that if I do a load from the highest memory address, what it really does is load from a keyboard, and if I say save to the highest address, it really sends the character out here to the display. But anyway, with that little 4-instruction computer, we can do things. Right now we've got a hello world program in here. If we restart the clock, we've got to reset the program counter. So actually, I guess since this actually modifies my program, I better reload my program too. So we'll reload hello world. We'll tell it to start running. And then you can see do hello world. It's a programmable machine. That means we put instructions in memory and it processes those instructions. So if we change the instructions, it does something totally different. Okay. So there it's saying hello world, hello universe. We'll put in a little program here to show nested loops. So here's some nested loops. What I'm going to do is just draw asterisks. And we're going to draw asterisks by looping. And it's kind of cool. We can loop with just one, I just have one conditional kind of thing, and that's that I jump if the accumulator is not 0. So I have to set things up so that when I want it to stop the loop, the accumulator is 0, and then we'll go up there. So anyway, if we tell this one we reset the program counter, so that we point to the start of the program, we reset the clock so it starts ticking, it will run this program. So it says, please enter 2 digits. What we're going to have is the first digit's going to be the number of rows, I believe, and then the number of columns. So if we say 6, excuse me, I guess I've got to enable my keyboard here. We'll put in a 6 and then a 7, and then it should go across here 7 asterisks and go down 6. So we'll scroll up. But anyway, it's just to show with only 4 instructions I can do things like nested loops. So let's talk about a little bit about how a CPU works, okay? How many of you want to just spend some time on this? How many want to actually look a little bit about binary binary numbers, digital logic? That's kind of what I prepared was from the beginning But if you feel like you've already got that handled, we could stay at a higher level, I guess. We'll go into the presentation. If it looks boring, just say, speed up, okay?
Will we be able to get a copy of this by chance?
If you'd like, we should do it.
Okay, thank you.
And there are actually earlier ones. If you want to play with a 16-bit one, you could talk to Matt, who's one of my students at Point.
What is the program that you're using for this?
This is a thing called Logisim. By the way, up here I have some little brochures. This is, it says Digital Understanding Computers in 2 Hours. It's a thing I would like to take around to schools and other kinds of things. So if someone would like to find out about it, there's those. I've got some business cards up here too. But on the back of this, it talks about, if you pick one of these up, it talks about the logic simulator uses and gives a link. It's called Logisim. It's free and open source. It'll run in Linux or Unix or Windows, iOS, Mac OS, excuse me, not iOS. It'd be nice to have it in iOS, I guess. Okay, let's go over this PowerPoint presentation. One of the things that I think is kind of cool about digital logic and about this logic simulator itself is that you can do all kinds of stuff with digital logic. We call these machines computers. In fact, we have a lot of things we call computers. I think that's really a bad name. Computers were these people that used to calculate logarithms and all that kind of stuff with adding machines. These are really programmable machines. They do a lot more than just compute. They browse the web, they do Facebook, they play games, as well as compute if you want them to compute, okay? They do things with digital math. The guy before was talking a little bit about analog and digital. Analog, I can make a transistor. If it just has to be on or off, the transistor doesn't have to be nearly as precise as if I'm trying to do analog things. And so I can make them small. I can put 3 billion transistors on a little chip. Each digit's twice the value of the adjacent one. We can combine these ones and zeros into big words, 32, 64 bits. Each digit's twice the value as we go to the right. In 10, we multiply by 10 each time. In binary, we multiply by 2 each digit we go over. So if we have a 32-bit word, we can have integers that go up to 4 billion or plus or minus 2 billion. If we have 64 bits, we can go up to a huge number, 1.8 times 10 to the 19th. There's a story they talk about a guy that saved the king's life, and the king said, "You can have whatever you want, up to half my kingdom." And the guy says, "Oh, king, I don't want much. How about a grain of rice for the first square on a chessboard, 2 grains of rice for the second square, 4 grains for the third square, 8 grains for the fourth square, and so forth for all the squares on a chessboard." Well, how many grains of rice is that? It's about that many. There's not that many grains of rice in the whole world. So the king was really embarrassed that he couldn't meet his obligation. One story says he cut the guy's head off because he couldn't fulfill his obligation. Probably should ask for maybe 32 squares instead of 64. You know? They might have had 4 billion grains of rice. Anyway, the reason the computers use binary is because binary is really easy. How many of you struggled? When I was in elementary school, 6 times 7, I'd have to say 6 times 6 is 36 plus 6, 42, It's hard for me, But these, the binary math, I got this down cold, 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, 0 times 0 is 0. Easy, okay? So when we use binary, it makes the calculations very simple. How many of you have seen the t-shirts that say that? There's just 1-0 kinds of people in the world, those that appreciate binary and those that don't. The reason is that number is 2, it's not 10. It would not make sense if you said there's 10 kinds of people in the world, those that understand binary and those that don't. But if you say 2 kinds of people in the world, then that's a binary number. Computers accomplish about 4 billion operations in a second. I had Matt do this calculation when he was in my class. If you said a human heart beats about, let's say 60 times a minute, times 60 minutes in an hour, times 24 hours in a day, times 365 and a quarter days in a year, times 80 years in a lifetime, you'd end up with something like 2.5 billion. So if you call the computer's clock rate its heartbeat, its little heart beats more times in 1 second than our heart beats in our lifetime, okay? So that's a lot of beats, right? In each operation it can store or retrieve stuff from memory. It's a programmable machine, so we change what's in memory, we change what it does. It turns out there's only really 3 kinds of fundamental gates. With these gates we can build anything. And in fact, we'll see that we actually combine normally when we build things, either a not and an and we call it a NAND, or a not and an or and we call it a NOR. And then we can build anything with just one thing, just as NAND or NOR. But anyway, what these are is they're fundamental gates. They're switches. If they're in series, I have to close this switch and I have to close this switch. So that's an and. And I got an and here someplace. So here's my and. I tried to make these look a little like the logic diagram circuits that you see. But anyway, if we want to light up the light, this one's for you, little guy. If you want to light up the light, you have to press this one and this one, okay? So that's an and. This one's called an or. With an or, I can press this one, or I can press this one, okay? So you can play with those and pass them around. So the or, the switches are in series. I can press this one, or excuse me, in parallel. So I press this one, or I press this one. Those don't seem like very complex things. And the not is just where we have a switch that's normally open. So the light's normally on. I push the button and the light goes off, okay? So it's just the opposite of what the button is. When the button's, oh, sorry. This one's kind of touchy, the light over here. Oh well, maybe we'll let you play with it yourself. Okay, anyway, the light's on, you know, press the button, the light goes off. Okay, so that's a not. This one's a little more complicated gate, but I can actually build it out of these other gates. This one's kind of like lights on your stair. Go up the top stairs, turn the lights off. Go to the bottom, turn the lights on. It's called an exclusive OR. I can press that one, the light comes on. Press that one, the light goes on. But if I press them both, the light doesn't come on. It's called an exclusive OR. It's kind of like you can have cake or you can have cookies, but you can't have both cake and cookies, okay? So you can try the cake or cookies. Okay, and so this is how you could build that exclusive OR with nots and ands and ors, okay? Here shows just how we could combine those to make nots, an and and a not, to make a NAND, or a or and a not, to make a NOR. We actually, places like I Am Flash up here at the point of the mountain makes our logic out of NAND, I think. So, anyway, this shows how we can take these gates and we can combine them to do fun things. Like, this is called a data latch. If we go back to this program, we could actually build one of these guys. Here to this, and we'll just say we want a new circuit. And we'll just build one of these data latches, unless you think that's too boring. Let's see, those were NANDs, right? We'll come back over here and look at our circuit again. Oops. Sorry. Our own things here. I guess I was looking for my PowerPoint presentation. So what we have, this is a NAND. You'll notice here we've got things cross-coupled. This is really the thing that latches the data. What this says, if a 1 comes in here, and if this is a 1 over here too, 1 comes in here, then a 0 comes out, 0 goes in here, then a 1 wants to come out, we put that back in here. So it feeds back to itself, and it latches the data. Okay, so that's called a data latch. We have here a button here that can write enable, so that will hook this data latch onto the input. And so we can put input in there, it will latch it, it will save it. This is how we do a memory circuit.
What
so
is latching?
Latching means like, you know, like on a cupboard, you have a little thing you flip and it stays tight. It means it stores data. What we're trying to do is see how a memory works, okay? So this is showing how we can just use these ands and ors and nots, the things we passed around, and make a data latch. Okay. By the way, maybe we should talk for just a minute before we do that. I've got a couple of other things here to pass around. What we're really trying to go towards is how a CPU works. So here I have a little CPU. This is a older Pentium, you know, one of the first Pentiums when Intel had their opcode problem, and they shipped out a bunch of them as keychains, I guess. So, but anyway, the current processors will now have 3 billion transistors on them. This is a little memory module. This was actually made in the factory I worked in Dresden, Germany. It's a 64 megs DRAM, so that means there's 70 million transistors on the surface of that. And that's what we're trying to do, is learn about how that stuff really works. Well, kind of the key to all of this stuff, just like that thing that I passed around, has switches on it. One of the first electronic switches was this thing right here. It's called a relay. What the relay does has an electromagnet. When the current flows through the magnet, it pulls this little iron thing down and flips a little switch that's over here. Okay. Trouble with relays is they take a lot of current to power the magnet, and they're relatively slow. I might get that to switch 10 times a second if I really optimize, maybe 100 times a second. But I could build something with that. And in fact, one of the very first computers had relays in it. I heard a talk one time by a woman named Grace Hooper, and she was saying that you know, that she worked with a computer that just had relays in it. They came in one morning, the computer wasn't working at all. By the way, these aren't very good computers back then. But anyway, it wasn't working at all, and they got looking at it, and they found a moth had died, and its leaf was underneath the relay contacts. So they pulled the moth out, taped it in the log book, and they said, "Bug found in computer." And that's where the word started. You know, we still talk about that a lot, but that was really truly a bug. Kind of the next electronic switches we use were these things called vacuum tubes. How many of you have ever seen anything with vacuum tubes in it? When I was a kid growing up here in Orem, we had a TV that had 27 vacuum tubes in it. And when we got it, you know, we watched Howdy Doody, Time, and Mickey Mouse Club. And then one of the vacuum tubes would go out and it'd quit working, and my dad didn't care. He didn't care if we didn't get to see Mickey Mouse Club until it got to be conference weekend. And then he said, "Okay, we got to get the TV fixed." So we pull all the vacuum tubes out, take them to the tube tester at the grocery store, find the two that were bad, you know, put them all back in the TV, and it would work for another 3 months. They were okay. I mean, they could switch pretty fast. The problem is they have to have about 100 volts to work, and then they have to have a lower voltage to heat up an element in there, like a light bulb. And so they have to have a lot of power. And it's kind of hard to build an iPad with one of those, you know. I'm with a few million of those because it just doesn't fit, okay? The big breakthrough was in 1947 at Bell Labs. They invented the transistor. A transistor operates at battery voltages, 3 volts, 5 volts, 10 volts. And then Bob Noyce and Jack Kilby took the transistor and they integrated them into integrated circuits. So now we can put, you know, thousands, or in this case maybe millions, current microprocessors, maybe 3 million transistors on the surface of a little chip like that, okay? So anyway, that's kind of what these switches are all about. Switches that make up ands and ors and nots. Those things are just either going in series or parallel. So we won't try to build this, but we could build this in that little logic emulation circuit. I would encourage you to do that if you're really interested. But what this does is, if we have a 1 over there, we push the button. Now there's a 1 latched. We can flip the data switch all day, and we'll stay a 1, okay? Until we press the right button again. And this is what we build things out of. So when you see something like that program counter in my little CPU, it's 8 of these things hooked together to make a 8-bit data word. And what I do is we bring in data when we want. When we want to store that data, we essentially do this push button, you know, write data into that memory. This is talking about how we actually do math. Did we ever find a pen? I guess we didn't.
No, I'm sorry.
I was gonna, if we had a pen here, we'd work this out. We'd just do a little math problem in binary. But in binary, you know, we build words out of you know, 32, 6, 8. We would have done a 4-bit one up here just for fun, where we put in some ones and zeros, and we see how it adds up. Okay, we could do our math in binary. In binary, if we have 1 or 0 plus 0 plus 0 is just 0. Why do we have 3 inputs? Well, we have to have carry because we've got these big long numbers, so we carry from the first stage to the next to the next to the next. Anyway, 0 plus 0 plus 0 is 0. If we have 0 plus 0 plus 1, that gives us a 1. If we have 1 plus 1, we get 1, 0. What's this number right here? 2. Yeah, this is binary for 2. If we have 1 plus 1 plus 1, then it's like 1 carry 1, so we carry 1 over here. Okay. We can put that into what we call a truth table. And what this says is, if they're all zeros, the carry out, which is this digit, is 0, and this digit, we call the sum, is 0. We can look at what all the possibilities are. If it's 1, 1, 1, then we have a sum of 1 and a carry out of 1. We can take that and put it into this little logic emulation package. We'll do this for just a second and build a circuit with it. Let's try this just for fun. We've got a new circuit in here. Let's tell it we want to build a sub-circuit in our project. Add a circuit. We'll call our circuit an adder. And then for our sub-circuit, let's tell it we want to analyze the circuit. So we haven't really built anything yet, but we want it to have 3 inputs. We want it to have an A input. That's one of our numbers. We want it to have a B input. That'll be another number. We'll want it to have a C input for the carry input. What's going to come out of this little adder? Well, we're going to have a sum. That's the bit right under the number, the sum. And then we want to also have a carry out, C out. We'll add those together. We'll tell it we want to have a truth table here, and we'll populate this truth table. So what's 0 plus 0 plus 0? 0. 0 for a sum, 0 for a carry out. What's 0 plus 0 plus 1? 1. So the sum is 1. Oops, excuse me. Should bring a mouse along so I could work these better. So the sum is 1, but there's no carry out with 1 or 1. If we have 1 plus 1, then the sum is 0, but the carry out is 1. That's 2. Here we've just got 1 again. Here's the sum is 0. Here we've got another. Is that right? So here we've got a 0 and a carry out is 1.
Wait, why is it 0?
Because 1 plus 1 is, you know,
2.
2, so
Oh,
it's
yeah,
a
yeah.
0 here and we carry out 1.
Yeah, I'm sorry, thank you.
Okay, 1 here. And then we could put if we have 1 plus 1 plus 1, then the sum is 1, the carry out is 1. We can say build a circuit, and this says, okay, if we want to build for that truth table, I will call it an adder. So we want to replace the circuit we've got there. So here's a circuit that can add 2 numbers. It's one of the things that's cool with this version of Logisim is we can just magnify right down there like that. Cool? Anyway, so what this is a circuit that will add 3 bits and tell us whether it's, you know, anyway, we'll just try this. So we come up here and I grab this little finger up here that can press buttons. And we'll, right now, if we've got 0 plus 0 plus 0, the sum is 0, the carry out is 0. If we put 1, 1 in there, now the sum is 1, carry out is still 0. If we put 2 in here, 1 plus 1, now the sum is 0, we're carrying out 1. And then down here we could have sum, carry in, carry out. Anyway, now we've got 1, 1, which is really binary 3, right? And so that can add a 1-digit number. Now what we can do with digital logic, and this is a really kind of fun thing, is we can come back here to our main circuit, and we can pull in some of these things like an adder. Put one down here. This is our adder, so it's got an A input right there. a B input down here, a carry input right there. Over here is a sum output, and here's a carry out output. So we could wire up stuff to this. Here's some push buttons. So we'll put an A input down here, and another B input down here. And we'll wire these up to this circuit. Wire over here to this one. And we'll take our sum and we'll wire it down here to an output. You might say, why is it red? Well, it's red because it doesn't know what it is. Normally it would be either dark green if it's 0 or light green if it's a 1. But we've only got 2 of the 3 inputs hooked up, so since it doesn't know what that is, it doesn't know what this should be. Okay. Then we could take that thing and we could replicate it and make a 4-bit adder or a 6-bit adder. We'll just make a 2-bit adder because we're going to try to be fast here. So we'll pull that, oops, I guess I need to say copy, and then we'll paste it. And now we've got another one of these. We'll slide it over here. And we'll take the output of this one. This is our carry out. And we'll carry that out into this node right here. And we'll take our carry out from here and we'll put it to another, so we can just see what the carry out is down here. What's the carry input to our first stage?
0.
Yeah. We don't have anything to carry in because there's nothing on the right to carry in. So we need to put a 0 into here. We could do that by coming over here to our wiring. We could say, let's just ground this pin of this circuit right here. And our ground is really a 0. And we can have a 0 come in and then our circuit would work. Okay, so 0 plus 0, 0, 0, 0, that's 0, 0, 0. So anyway, those all add up to zeros, right? If we have 1 come in on one of these, 1, let's get our finger over here so we can add in here. So there's a 1. If we have another 1, 1 plus 1 is, what's 1 plus 1?
2.
Yeah, so there's our binary 2. Yeah, 2. What's 1 plus 1 plus? Well, let's see. We wanted to have 3. I guess if we make one of these a 0 and one of these a 1, now we've got 1 plus 2, because that one's 2 in that column, so now we've got 3. If we have 3 plus, I guess this would have been 3 if we would have put that one there. So there's 3 plus 0, which is 3. If 3 plus 1 is now 4. So now we see the 4 there. We make 3 plus 3 should be 6. So does that look like 6? Well, this one's times 1 times 2, so this is 2 times 4. So this one's 4 plus 2 is 6. So we can add, right? Let's go back over here to this PowerPoint presentation and we'll try to get through this a little bit more. Okay, so we can build circuits. We can combine them to make 4, 8, 16 bits. Here's a little how we can build an encryption with exclusive ORs, but we won't spend time on that. Anyway, what we really want to try to get to are microprocessors. We want to understand the microprocessor. Microprocessors contain billions of transistors. One of the books I used to use is Dave Patterson's book. That's Matt's book too. I guess we use Linda Knoll's book right for your class. Anyway, he says a CPU is a data path and control circuitry. It includes storage elements, registers, combinational logic like adders, ALUs, loads instructions from memory and accomplishes the task. This is what we call a von Neumann architecture. Unique feature of von Neumann architecture, and this is what all of our computers we use now are for the most part. There's a few processors, microcontrollers and things like the PIC version and use a different architecture, Harvard architecture, where data is in one memory and instructions are in a different memory. But for the most part, we use this von Neumann architecture where there's one memory. That memory contains both the instructions for the processor and the data. Okay? And that's kind of cool. Inside, so this is the memory. Here's the CPU. Inside the CPU, there's a register. This is 8 bits, 16 bits, whatever, depending on the size of the computer. Program counter. This keeps track of what instruction we're going to run next. Normally, when we start the processor, that program counter goes into the memory address buffer, into the address bus, into the memory, pulls out a value out of memory. We take that value, I guess I should have had another arrow coming back over here to the instruction register. We take that instruction from memory, we put it in the instruction register. The instruction gets split into two parts. A part that tells what the instruction is, and a part that tells what we're going to do the instruction to. Okay? And in this case, it's an address. So we'll take that address, we'll go into the address bus, we'll get data out. Sometimes we'll do a load from memory into the accumulator. Sometimes we'll take what's in the accumulator and we'll save it into memory. Sometimes we'll take a value from memory and we'll put it in this memory data buffer and we'll add those two together and we'll put it in the accumulator. The other instruction I have checks to see if the accumulator is not 0. If it's not 0, it loads the value of that address into the program counter, and then we start running instructions there. So that's like a jump instruction. So it can jump to a new location. Okay? And then we have those input and output where if we say save to FF, it will actually take what's in the accumulator and send it to the output. If I say load from address FF, it will put the thing that I type on the keyboard into the input buffer. Let's see. So here's the instructions my little computer can understand, just 4 instructions. Load is get a number from memory and put it in the accumulator. Add is add a number that's in the accumulator to something that's in memory. Store is copy the number from the accumulator into a memory location. And then the jump accumulator 0, not 0, I guess NZ. If the accumulator isn't 0, then we're going to jump to the address that we give with the instruction. Okay? And then I've memory mapped 2 I/O commands. So if I say load with an address that's the highest, 8 ones, and then it will load from the keyboard. If I say store to address FF, all ones, it will store to the output port. So here's a quick overview of my processor. So here's the parts. Here's the program counter. There's some logic along with it. This is so that you can see the value in binary, or this is hexadecimal right here, so that says hexadecimal 52 is really that binary number. There's 2 things that can come into the address buffer. One is the program counter. The other thing that can come in there is the other half of the address half of the instruction, the address 8/10 of the address of the instruction can come in here. So we have a multiplexer, so we can choose between the program counter or that that part of the instruction goes into the address buffer. Here we can see that value, and I guess here it's hexadecimal. Up there it's hexadecimal, but bigger if you want to see it. That goes into the memory, tells us what we're going to get. When we select the memory, the first thing we do is we load that into the instruction register, split out the address and the opcode part. Depending on, this opcode comes in here into this thing. This actually decodes the instructions and automates the processing of the instructions. So each clock cycle will do part of an instruction. In this case, each instruction, takes maybe 4 to 6 clock cycles to do an instruction, depending on which instruction it is. So as the clock ticks, we'll do parts of an instruction. In really advanced processors, our x86, they do a thing called pipelining. So even though it only does part of an instruction in each clock cycle, it will be doing a whole bunch of parts of instructions in parallel. So it can effectively get an instruction out every clock cycle. Okay? And then here's my keyboard input and the data output. Anyway, quick overview of the processor. instructions, we've looked at those again already. There's some things that are kind of rules on the data path. I guess we would better not spend time on that. This kind of shows the steps that happen each time we process an instruction. So that instruction decoder does these things. First thing we do is take the program counter and put it into the memory address register. Then we take the memory contents at that location, put it in the instruction register. Then we increment the program counter. And then, depending on what the instruction is, we'll do these other things. So if it's an add, then we take the address part of the instruction, we put it in the memory address register. We grab that value that's in memory at that location, we put it in the memory data buffer. We add hook the accumulator up to the, the arithmetic logic unit to the accumulator, so we add those two numbers, the one that's in the accumulator and the one that we just put in the memory data buffer. Okay. If we do a load, we put the address in the memory address register. We grab that value from memory and we put it into the accumulator. If the address happens to be FF, then we, instead of grabbing from memory, we'll grab it from the keyboard and put it in the accumulator. Okay, the store, it's the opposite. We take the address, we put it in the address register, and then we take what's in the accumulator and we put it in that location. If that address happens to be FF, we'll write it to memory, but we'll also write it to the display. And then this one's a pretty short instruction. If the accumulator is not 0, and we give this jump instruction, then we'll just take what's in the address register, the address part of the instruction register, and we'll put that in the program counter. So then we'll start running from that instruction. So a really simple little processor. So here's a picture of it again. We've looked at it. Let's run another little program, just to show you how this thing can work. Okay, so here's our computer. We'll load a program in here, load image. Here's one that's called name, please. We'll clear our terminal right here. If we want. We'll reset the program counter, so it's got to start at the start of the program. Then we'll reset the clock so it starts ticking again. So now it's running. We can come up here if we want with this little tool and we can say simulate. We can pick a clock frequency. So if we pick a low clock frequency, I guess we'll wait till it's actually running. Or we can pick a high clock frequency. If we have a high clock frequency, it'll run faster. Need to enable my keyboard by clicking on it. Now when I type on my keyboard, it will process those values. Timothy. Hello, Timothy. Pretty cool, right? So we can do real stuff with this little 4-instruction computer. What do the programs look like for this? Wish we had a pen up here and we'd try writing a little machine language program on the fly. Let's load one more in here. Load image. Call this one's a formatted add two numbers. So we need to reset the program counter, so we're pointing to the start of the program. We'll turn the clock on here. Okay, so we're going to put in some numbers. Hey little guy, tell me one digit number. 2? You try 2? Okay, so here we got to enable our keyboard first. I should let you come up here and try this. So we got a 2 there. It says 2 plus. What should we put for this other one? 5? Okay, let's put 5 then. 2 plus 5. You tell me if this works right, okay? Oh, 5. Okay. 2 plus 5. Can you see that from where you are? 2 plus 5 is? 7. You got it right, didn't it? One of the problems we have here is, what do we have to do to make that happen? Well, we have to convert this 2 into an integer from a character. And then we have to save that character because we don't have other places to store it, so we have to put it in memory someplace. Actually, let's just look at the program to do that. This may not be exactly this one. This one may be a little more simplified. Let's come over here. Add two numbers. So this one's not actually doing the formatting, adding the plus sign and adding the equal sign. Well, that's just a couple of extra steps we'd have to stick in here. This is what we have to do. We have to say 1FF, that's load a value from the keyboard, right? 1 is the load command, FF means from the keyboard. So we load the first number. We want to see the number that we type in, so we have to do a save now. So that number we just loaded is in the accumulator. This one saves what's in the accumulator output, so then we see the number. We want to convert it from a number into from a character into a number. Okay. How do we have to do that? Well, we have to subtract an ASCII 0 from the character. Well, I don't have a subtract command, right? So what do? Well, I add the negative of an ASCII 0. So ASCII 0 is 30 hex. The negative of that in my little 10-digit number is 3D0. I guess that should have been a 0 instead of a, maybe it is a 0. And that's kind of confusing. It looks more like a letter maybe than a number. But anyway, so we don't have a command that says add the negative 30. We have, okay, thanks, 5 minutes to go. So what we have to do is put it in memory someplace. So we put it in memory location A. This is just hexadecimal, so we go up to 9. We want to have 1-digit numbers here, so instead of putting a 10, that would be a 2-digit number. We put an A, B, so that's how hexadecimal works. Anyway, so this location, so we say add this negative ASCII 0. So it adds from what's in memory location A, which is this thing. We add that to the number that we just got. We save it in memory location. 2 is a save. 0B, that means save in this memory location. So that's where we save the first number when we've converted it from a character into a number. And then we get the next letter by loading from FF. So that gets the second number. 2 saves that number to the output. And then we add from memory location B, so this is where we save our number. We add that to the value that we've got, and then we send that to the output. Why don't we have to convert the second one into an integer? Just be an extra step. We'd have to convert it to an integer, add them together, and then we'd have to convert it back to a character. But if we just add on to a character, then we'll go down the ASCII table, and it does some funny things. If we try to do something like, I don't know, if we try to do 6 plus 7, so 6 plus 7 is an equal sign. And that's because we don't have a character for 13, or for, I guess that should be, 13. We don't have a character for 13, but that character that is 13 from hexadecimal 0 is an equal sign. So anyway, if we had multi-digit numbers, it would be a lot more complicated program. Okay, let's come back over here. So that's kind of how we have a program. We save the output, and then we jump to the next program. If we did happen to calculate something that gave us ASCII, hexadecimal 0, excuse me, then we wouldn't jump, and then here we'd just stop and wait for an input. Now here's another little program that shows how Hello World works. One of the things that's a little bit of a problem in a computer like this is we don't have indirect instructions. So I could say something where I just say, print H, print E, print L, print L, print O. But that won't be very exciting. We want to use loops and do other kinds of stuff. So what I do in here is I load the location in the first character. So down here is just characters. So here's my H. So this says load from memory location B, which is the H, into the accumulator. We output that to the display. And then, this is the really tricky, subtle thing. Here I'm going to load the next character. I load that instruction into the accumulator. I add from memory location 9, which is a 1, add 1 to it. So I increment that instruction. Self-modifying code. Okay, increment the instruction, and then I store it back to memory location 5. So now I've modified this instruction, so now it says 10C. Now I'm going to load the next character, and then I'm going to check. When I get to the end of my hello world, hello universe, I'll have a 0 down there. So if I load that 0, and I say jump if the accumulator is not 0, the accumulator will be 0, and we'll just stop. Okay. Anyway, that's how that hello world program works in my little computer. So, let's see, we got a couple of minutes left. Memory can contain instructions or data. Data could be integers or numbers or other kinds of things. The program has to keep track. Computers are really neat. They're programmable machines. They use digital logic. What does digital logic consist of? Ands, ors, nots. Okay. They accomplish tasks. The instructions come from memory. They're processed by a CPU that consists of a data bus and control circuitry. They're complex machines, but we can't understand them, and they're in everything. How many of you have 5 computers on your person right now? Maybe? I don't know, maybe 3 or 4. You might have a phone and a computer, and I don't know, maybe you're carrying all these around. Maybe sometimes you have more than one. I don't know, I have an Android because I want to learn about Androids, and I have an iPad and an iTouch and a Windows 8.1 tablet and all that stuff. So anyway, we use them all the time. They're in everything. They're in our cars, they're in our washing machines, maybe even your blender. Okay? So here's acknowledgments. I want to acknowledge many students I've worked with who I've learned from. That's one of those. Carl Birch, he's the author of Logisim. I think it's a really wonderful logic simulation package. You can do all kinds of experiments if you're into hardware. You can do hardware experiments without smoking. Okay? And George Mills, he wrote another one I think is kind of cool that I use, and actually built some CPUs and call them all immune logic. Anyway, anybody have any questions? Pretty cool, right?
Mm-hmm. How do we get your slide deck? If we can.
Send me an email and ask them for it. So.
Thank you.
Yeah. I guess got BYU Hawaii card here too. If anybody wants my address, BYU Hawaii, which doesn't work anymore.
Did you just recently retire? Or?
No, I came here 4 years ago from Hawaii. I got this note from BYU Hawaii, and it says, you're eligible for an early retirement if you want. I don't think they wanted me to retire, but and it wasn't that great of an early retirement package. But my son, who lives here in Orem, says, Dad, there's an open position at UVU. I said, okay, I'll give him a call, Anyway, I called him up Friday. They said, technically our position's closed, but give me your phone number. If we don't have a good candidate, we'll give you a call. Monday morning, I got a call bright and early at 9 in the morning. They said, how fast can you get an application? And I said, give me a half hour. So I dropped an application in their system and called back about 10 minutes later, said, can you come in and interview tomorrow? And I said, sure. So I went and bought a suit, got my hair cut, put together a presentation, went in and gave it, and they said, we need to know in 2 days if you'll take the job. So I called BYU Hawaii, and I said, I know I signed a contract to teach, but I just got another contract from HR that says if you'll quit by the 1st of September, we'll give you extra pay. So I said, I'm going to do it. So I came here. It's been in a temporary 1-year position. I'm now on my 4th temporary 1-year position, and they tell me they want me this fall too. So.
Which department?
I'm in computer science.
With Kirk Love and all those guys?
Yeah, with Kirk Love and those guys. Yeah.
I teach in Infosys.
You teach Infosys?
Yeah, people.
Where's that again?
It's on 6th floor.